Hello and welcome to another video from KOJRO. And I do understand that the numbering of this video is kind of confusing. This will be 9.1, I can call it, in the Resurrection series. And episode 9 in the Resurrection series is all about the power supply. And in the first part we took apart and from the C64 C area of computers, and we started to measure on this, and we drew up the schematics and we analyzed what's wrong with that power supply. But in this episode we are going to do some theory about how the regulators work. We are also going to do some calculations and stuff so that you understand what's going on in this kind of power supply. And I also got some comments about that they replaced this with a modern switching regulator, and of course that's the wise thing to do, especially when you see the math behind this kind of power supply in real life. It's no surprise to me that this is quite the good foot warmer, as it's a lot of heat dissipated inside this tiny box. But let's start with a walkthrough of the 7805 schematics and also the part that is most rumored to be inside these Powerbricks, although I have not get that confirmed. There are lots and lots of producers of the 7805 family of chips, but I go to one of the original supplier of this, and it was Texas Instruments, National Instruments, Toshiba and some other brands that had this originally. Also Motorola had this part from back in the day. But this is Texas Instruments' most recent schematics, and they recommend that people use the LM340 part instead of the 7805 part because it's more accurate. And here in the description they actually states, if adequate heat sinking is provided, they can deliver over 1.5 amps output current. So adequate heat sinking. The packaging this is available in is all these, but the case used in the C64 is this TO220 package. The TO3 package is also known to be used in the long and short board versions of the 1541 drive. And this is able to handle more heat, and it also has a larger area to spread the heat about, but the die inside this is actually further away from the metal can and so on, so it's a bit of a trade-off there. And we will just scroll through this, and this is the packaging information, and here we can see that this is clearly the way things are on our C64 power supply from before. This is the input, the GND or reference, and output. This is the way that it was in the demolished Powerbrick. Yeah, and we come to some absolute maximum specifications and so on, and they also have some characteristics about the temperature range of the different pinouts and stuff, but I will only show you one diagram for this, and this is the LM340 part, and we will jump through that and we will go to the common specifications for the LM340 and LM7805 part. And here you can see that all the measurements is done with a junction temperature, and this is the internal temperature of the component of 25 degrees. They have stated that this is valid for a current draw about from 5 milliamps to over 1 amp. They say that the minimum voltage is 4.8 volt and the maximum voltage is 5.2 volt. And here you must remember that even though the nominal components do output 5 volt, if one of these components output 5.2 volt and you have also raised the voltage by having this voltage divider on the reference pin, you can risk that this actually will give out 5.4 volt into your circuit, and that is approaching a dangerous level for a lot of the components in the C64. But of course you will lose some in the cable and in the plugs and so on. And we can also see that the minimum input voltage to this is 7.5 volt. And there are some other numbers here that is wise to notice, and that is the short circuit current and peak output current. So this can deliver a peak output current of 2.4 amps, and it can deliver 2.1 amp into a short circuit. That means that probably if you have an infinitely big heatsink or cooling, you could use this to supply 1.7 amps, but you will be running the component on a maximum load all the time. This one was the one that I wanted to show to you. Here it's stated that this chip or this part is able to dissipate 20 watt of power with an infinity heatsink. That means if you have a heatsink that is big as a car, you can get away with this part dissipating 20 watts of heat. With a more moderate heatsink that is able to dissipate 10 degrees Celsius from 8 watts, you can have from 10 watts to about 5 watts on this. And you can see here the ambient temperature is the temperature that the heatsink is dissipating its heat to. And the higher the temperature are, the bigger the heatsinks needs to be to get the excess heat ventilated away. And with no heatsink at all, it's just 2 watts or something that you can draw from this part. But with a good heatsink, you are able to have something in this area dissipated in this power supply. And this is wise to remember when you should do the calculations later. And I just scroll through this to come to this schematics for this part. And you can see here, this is the voltage in, it's up here. And this is a series regulator transistor that is in an NPN variant. You have one series resistor here on 0.25 ohms. That actually is a current detecting resistor. And it's this resistor here that makes the chip able to detect how much current goes through this circuit. And that is amplified by Q14 here and delivered into this network and stuff of things. And down here you have the constant voltage source and so on. I won't go into details about this. But in reality, you have the input voltage, you have a series regulator, and you have the output voltage, and everything is referenced to ground. So that is basically this circuit, and although there are a lot of differences between each manufacturer's 7805, the ground premises are the same along all the different parts. And here you have an example that, reminisces or in some way, because you have this resistor network from the output to ground and the reference pin is connected between these. That is how you do the raising of the voltage on the bottom, and this is according to our schematic. And here you actually have an application example that looks a lot like our circuit, except that you have the voltage divider part here. You have a twin output transformer with the middle junction point for the windings as a zero reference point, and you have the 2 diodes here put together and into the input. You have a reference and you have the output. That's it really. But now let's take a look at another regulator that has slightly other specifications. The rumor has it that it's not an 7805, but a SI3052P that's inside the Powerbricks from Commodore. And I can at once say that in the old ones, the footwarmer kinds, it's not this chip. I have seen 2 different chips in this, and they have all been variants of the 7805, but with some small differences. If this is the chip that is in the modern bricks, it can explain some things. The main thing is that it is stated that the power output on the 5 volt rail is 1.7 amps. And this has a current absolute maximum of 2 amps. So that is a possibility. The other 7805 series has a maximum power output of 1.5 amps. at least the normal serial production kinds, and most of them only have 1 amps. And of course this depends on how much heatsink you have. I will get into details on how this has to be calculated in a short while, but we will see in some of the ratings here on the datasheet. And as you can see here, the power dissipation, it's how much power this can dissipate with a heatsink and without a heatsink. And without a heatsink it can only dissipate about 2 watts. And it can dissipate about 50 watts with a thermal surrounding temperature of 25 degrees Celsius. And also you have to have a heatsink that's about infinity size to reach this. And you can see that it has an operating temperature to about 80 degrees before something goes wrong, and the absolute maximum temperature before the core in this collapses in 125 degrees Celsius. And this package of this is not a TO220, it's a TO3P package. And they look about the same, but this is a slightly heavier package with more metal and better heat conductivity. And the output voltage of this is typical, of course, 5 volts and can range between 4.9 and 5.1. This is about the same as a 7805. We can also see some other interesting figures here, that you need a minimum voltage of 8 volt for this to operate, and the absolute maximum is 30 volt. You can also see that the overcurrent protection starting is 2.4 amps, and this is also measured with T volt input. I don't know how this current limiting feature, how this reacts with more input voltage. And the schematics for this is slightly different from a 7805. It's much less complicated, but it do have the same features as voltage source. You have some current limiting capacities. This is also a normal serial regulator inside here with R1 as the measurement component to measure the current output. And that's also numbered in the terminals on this one. It has the output is on 1, and that the input is on 2, and that the reference or ground is on 3. And this is clearly not the case for our regulator in our Powerbrick, because our is configured as a normal 7805. On our circuit we do have that the input is 1, number 2 is ground, and number 3 is output. That is confirmed by my schematic. So if this is an exact part, it can be a specially molded part for Commodore, can be another chip with similar conditions. At least we do hope that it's not a regular 7805 that's not able to handle this kind of current. But at least we can see the chip that is supposed to be here, the SI3052P, has a wrong pin out to be the one appearing in our Powerbrick. I will try to take it out and see if there is some writing on it, but I have tried this on one other power supply and I was not able to read anything of this chip afterwards. The epoxy has fastened itself to the surface, so when I took off the epoxy, every part of the writing was, either it was never there or it was not readable. So let's just take a quick recap of what we are measuring here. I have the 7.1 volt, so now we have recreated the fault from before. And here we have the original 8.67 volt or 8.6 or something that we had. It varies a bit with the input voltage from the mains. And this is still a bit all over the place, and that is because there is no capacitor here, and this has a very slow sample rate. So this depends on where this samples on the sine wave, and we have no capacitor on the 5 volt rail on this board. So what we have here now is that we have no filtering capacitor inside the circuit. These small ones might be working, we have not measured them, they are not short-circuited or anything, but they might have lost their capacitance. And we also have the faulty voltage regulator that's just acting as a series resistor. The reason why I say that is that we can see there are some difference in the power from the input to the output, and it's about 2 volt peak to peak or something less when we take the RMS value. And of course this voltage is absolutely damaging to your C64. It has a peak voltage from 0 to 12 volt, and that is absolutely not good for your C64. So even though you measure this at 7.1 volt, you absolutely have a real devastating voltage into your C64 with this power supply. So Tommy on Arctic Retro did a very wise move when he did not connect his C64 to this one. And on the input we have a 14 volt peak to peak voltage, and the Schematics measured this to 8.6 and 7.1 volt. And why is that? I can't get the calculations on this quite to fit, because normally you take the peak voltage here and you divide it by the square root of 2, and the square root of 2 is about 1.41, 42, 136 or something. That should be a slightly higher voltage from both of these. It should be 9 to 10 volt something and 8 to 9 something on this, just doing the calculus in my head. So we have to bring in the Flux scope meter to see if there is something wrong with the RMS measurement on the Schematics voltmeter. Yeah, so what with the volt and everything, what we see when we do a calculus on this is that you have the voltage in, RMS value should be 9.9 volt when the 14 volt 0 to peak value is there, and the output should be 8.5 volt with a 12 volt peak voltage. And of course this might vary a slight bit between each measurement because of the difference in the mains voltage that's fluctuating a bit. But we measure a voltage that's slightly lower than what we expect. We are showing 8.6 volt and we should have about 10 volt. And we are measuring 7.1 volt and we should have 8.5 volt. So why is that? And that you can see here on this picture from the scope, and this is the same one that's up here. I've only enhanced and marked out the important bits here. This is not a perfect sine wave. By no means, because this pulse that you have over here on the top half is round and a good sine wave. But on this one, you have a pointed curve on this, and this might be to capacitance, and it might be to some other artifact that's shaping this part of the waveform. But this is confirmed when we look at this on the scope meter. So this is how this curve looks, and that is why you have a lower voltage. Because on a total sine wave, when you are measuring RMS, you are measuring the area inside this curve. And when you see that half the curve is much smaller than this one, of course you will get a lower RMS value. And what we can see here is that the curve here is not a totally good sinus. You can see that this is shaped like with a pointy end down here and kind of a more sinus up here. And that is why we don't get the expected voltage out of this, because when we measure through RMS, we actually measure the area contained within the curve. And this is the input, and we measure 8.6 volt, while our mathematics tells us that we should have about 9 something volt. And on the output we do measure 7.18 volt, but you can see the peak to peak is the same here. You have a rounded curve up here and you have a sharp point here. And you can also see that every line traces 0, because the 0 line is in the middle here. When you touch it like so, you get the from 0 and up on both sides. And if I'm going to measure just straight above the voltage regulator, I will find what voltage drop there is over this regulator. I can measure the right way, so I get the curve as a positive one. And you will see here that is 1.48 something volt dropped over this. So this acts just like a resistor would do. So our trusty old Schematics actually was right, and scope meter confirms this to us. And also when you look at the scope picture, we have confirmed that this is the way things are. But to top off this experiment, I'm going to solder in this capacitor, and this capacitor is an old one from Elco. I've had this laying around for years, and this is a new part. It's not been used. I've soldered it in once before just to test, and this is a 2200 microfarad and it's 40 volt. And even though this is very old, I do think that it's valid yet. It has never been used and it's a high quality component. It might not be wise to put this in a production environment, but for our test it will be good enough. Cooling efficiency of this epoxy really amazes me, because this should be a very easy soldering, but it kind of is not. I solder this now with the power on, and let's see what we got here now. I will stick this to ground again, and we just measure over this filter cap. And now we have 13.65 volt as an input to the regulator, and as output we can see here that our tester now gives us 11.4 on the output. And let's now measure the output and see what we have. And it's easiest to measure the output like so, just straight over here. And you have 11.26 when you measure with the flute. So this is good. And we can also check about what we have on the AC rail. And AC we have here. And now I have the scope on DC. I will just change this and measure the AC. Like so, and it's 11.2. So I do think that this is accurate enough for our findings. It's 10.7 something, and that is quite good enough. I can actually adjust this a bit to get it more accurate. 11.02. Like so. Now it's 11. So what's clearly is the case that the regulator have to go. And I will just desolder these leads, and I will hack in an ordinary regulator in here to see how this behaves. I will just desolder the input and the output terminals, and since this aluminium edge is still connected to ground, I have to be a bit careful with where I place the leads, but I think this will be okay just to solder in a new test part. By the way, this is the final schematics for the white C64C Powerbrick, and we have confirmed this several times now, and this is what's inside all of the Powerbricks that's sold in Norway, at least of this kind. And these three capacitor values we have not established, but when you have looked into the datasheet, this will probably be more than the 2000 microfarad that I estimated earlier. It's probably more close to 4000 microfarads. And this is probably around 220 nanofarads, and this is 100 nanofarad something. But any value between that will go quite good in these cases. And it's also stated that this one can be omitted if it's close to this one, and this one can be omitted if you have short power leads, but that we absolutely not have, so this one is expected to be there. And the values of this we have confirmed that they will give out a good voltage, and we will look into that again now. Yeah. Here I have a 7805, and this is an L7805CV, and it's made in China. And we have the input, the ground, and the output. So I'm just going to bend it a bit and give it a bit of a solder so I can just hack it into place. I will add now heatsink on this on the first tries here. Yeah, I do think we are okay here now. So I will just remove this a bit away from the capacitor. On all these 78 series regulator you have the ground on the heatsink. That I think is one of the ways that this is popular, because this is just ground. On the 79 kind of regulator you have the output connected to the heatsink. But now it's time to plug in and test and see if we got the expected 5.2 volt. And our tester says 7.2 volt, and that is not good. This was not something I expected. I do have a regulator here now, and I do have an output, and I do think I get everything isolated from each other here. I'm going to check with the scoop meter. This on DC. We have the input is still 13 something, and the output, yeah, it's 7.19 volt, but a DC voltage. And that means that there are something with the resistor network that is not quite okay. And what voltage do I have over this one? It's 2.29 volt over this resistor, and the other resistor, it should be this one, 4.89 volt. That's very strange, but I'm going to disconnect this again, and I'm going to desolder the middle pin, and I'm going to add that just to ground to short out the circuit. Yeah, I just use a short wire and I connect the middle pin straight to ground. Then this will be an ordinary 5 volt regulator that should give out close to 5 volts. And I plug back in. And now it goes to 4.9 volt. And now we have no regulator circuit other than the 7805 itself. So we are going to see what we have here. This is ground and this is the input. It's still the same. And the output is 4.88 volt, 4.9 volt. And that's within specification for a 7805. It has no load, and I can't load this down with the full load of this because it will burn pretty fast. But if I just take a quick peek like this, it doesn't drop the voltage, but the voltage of course drops in here because we have this thin wire here that should supply this. But so what's the mess and what's the secret with the resistance network that's not working? And we have two culprits here. We do have this capacitor, could be wrecking havoc, I'm not sure. And we have this one that could be short-circuiting something. So I will be desoldering this one first, and that I most easily do on this side. Yes, now I still have this one here connected, but this one is disconnected. Now the resistor network is back in, so let's see what's happening now. Yeah, we still get the 7.25 volt. We will try to disconnect the output capacitor from this too. I'm not sure how that most easily will be done, but I will try to remove it at this end, like so. Again, not the soldering contest, just to make things easy measurable. And now the output is just the resistor network and no capacitor. And we try again. It's 7.22. And that is might the way it is with a 7805. We will go back and we will check that. So we do know that the resistor network is causing this, and that might mean that this is not a regular 7805 and that the resistor network is different. Because when we measure on this one, and we can take this now on ohms. I hope that this is visible on the screen. Because when I measure this one, I can measure this resistor here, and it comes out about 97.8 ohms, and the other resistor is this one here, and it comes out as 3.6 or something, 3.5. Yeah, let's call it 3.5 ohms, and this about 100 ohms. So we do know that this works with the 7805 connected to ground, but it won't work with the resistor network that is meant to be working in this one. Yes, we have strange things happening to us all the times in this power supply, and this is really a puzzle for me that we have to dig deeper into. And this is the equivalent circuit, and this is from the datasheet for the 7805. And this is about the same situation that we have on our power supply, but we don't have a variable resistor on R2. And our circuit is that R2, as we say here, is 3.5 ohm-ish. I've stated 3.3 because that's a standard value. And this resistor here, R1, is 97 point something measured, and I said that this is 100 ohm. And that it's small variances and almost within specifications if this is a normal resistor with 5% accuracy, as was the norm back in the day. And this formula is the same that we used to calculate this earlier, but I did one omission and I also mentioned this last time. And that is that there is a current that disappears into the 7805, and this is the current that in the datasheet is labeled IQ. And that is stated in the datasheet to be 8 milliamps. And that means that the current that goes through the R2 resistor is 8 milliamps bigger than the one going through the R1 resistor. So if we take this into account to get it as exactly as we can, we have this formula, and this is also from the data sheet. And that is the voltage 5 volt added to the 5 volt on R1, and that is the current through R1, and this is added with the IQ, and that is again multiplied with R2. If we fill in the numbers here, we have 5 volt, and I have rounded the resistors to the values that we show in our schematic. It doesn't matter much because it won't give any big outcome on this value. And you can see that we have 5.19 volt, and that is spot on what we should expect. And we have measured these resistors in the power supply, and this measures about 3.5 ohms, and this measures about 100 ohms or 97 point something. And that means that we should really get 5.2 volt out of this regulator. It's according to the datasheet, and it's according to the values that we have here, that others have calculated before us also. But when we actually put the regulator into the C64, we get about 7.2, and that means that the current that goes through this resistor is much bigger than it should be. And the reason I know this is because the voltage here is raised higher than it should be according to what we expect. And there is one possible culprit here. You have the capacitor here, but that we have desoldered. So this capacitor is desoldered from the circuit. And there might be some other hidden capacitances down in the epoxy, but I don't think there are. So I really don't understand what's going on here. But I will find out, but that will be in the next installment of this series, where we try to reconstruct the whole circuit on top of the epoxy instead of using the components buried within the epoxy. And in the next episode, I'm also going to look into the thermal capacities of this epoxy, because I've seen that I can't burn this with the soldering iron, and I've put the soldering iron on 450 degrees Celsius, and I can almost melt something in this epoxy, but not much. And we see that when I put something on the epoxy or try to solder one of the legs that's deep into the epoxy, it's very good thermal conductivity because it cools the wires way down so that I get bad solderings. So that we are going to dig into in the next installment of this series. So hope you enjoyed this part. It was a bit technical, but it was meant to be. In our next part, we will build, as I said, a power supply on top of the other one to simulate the circuit as it should be from the factory, and we will also put in a modern switching regulator to show you how this would be. So the theory in the next installment will be about the power dissipation in these power supplies, and it will also be how we should remedy that in a replacement regulator. So please hit subscribe, like the video if you enjoy some of the contents that we have in here, and see you in the next one. And the next installment will be in a little bit over a week, because I'm doing some traveling the upcoming week.